All right, so this section is the dot product and the cross product. So again, a nice review of multivariable and how it's used in linear algebra. It's about the same thing since we're dealing with the vectors right now. So let me just talk about what this represents. Just a nice little review. So given two vectors, let's say this is A to B, this is A to C, those points. So given two arbitrary vectors, we have an angle between them. Right, so that angle is actually pretty important going forward, especially for the cross product and the dot product. But how we really define the dot product in multivariable and most important in linear algebra is this way. So given u and v, right, two vectors in two dimensionals, then the dot product of uv is denoted as u dot v, or just u times v, and we multiply this way, right? It's component to component plus each other, or in three dimensions, component to each component. But what really happens is this angle is what's most important, because that's going forward is going to be the key thing of what the angles within those vectors come into play. So when we're given an angle, or we actually want to find an angle going forward, we have this theorem. So again, given two vectors themselves, and theta within them, so the real dot product or equation looks like this. It's the length of each vector times cosine of the angle they make. Okay. So using this theorem, use just a little example to illustrate that. So let u equal that, let b equal this. We want to find the dot product between them. And then find, so first we're going to calculate this. Then we're going to find the angle between the two vectors themselves. Okay. So this one we could do both of them. We're actually have to use both equations anyways. Okay. So first we could find this. So we'll do u dot v. So using our definition of a dot product, and then we'll eventually use this one to get the angle itself. Okay. So first we'll just do component by component. So it's going to be 1 times -4 plus 0 times 1 plus -1 times -3. This gives you a positive 3 there. So our dot product is -1. Okay. So this part is -1. So now to figure out the other part, you have to do each one individually, and then we'll do cosine inverse to go backwards. So next we'll just get the length of each individual vector. Okay. So 1 squared is 1, 0 squared is 0, -1 squared is 1, so this is the square root of 2. -4 squared is 16, 1 squared is 1, -3 squared is 9. So this is 10, so it's going to be square root of 26. Okay. All right, so to answer this question, going backwards, right? So we found this is going to be -1. So be -1 equals these two put together. So that's the length of each individual vector times cosine of theta. Okay. I guess we could put these together. That's 54. Oh, sorry, 52. And then divide this over. And then we do cosine inverse of this. And that's the angle we want. You could plug in the calculator, or you could just leave it like that and give the proper notation of it, either in radians or the actual theta degrees itself, but that's good enough right there. Okay. All right, so like everything else, when it comes to dot product, what are the properties we could do with dot products? And it's mostly about the same stuff. So given three vectors with a scalar c, if we multiply u dot u, it's actually strictly greater than 0, which is ironically enough. And we go down the list. The nice thing is this is associative, and you can just flip them around. Same thing if it's a scalar multiplication, and it's closed under association as well, okay, which is nice. So that's, again, that's strictly for the dot product. Cross product is drastically different, but the dot product follows the normal multiplication rules itself. Okay. But what we care about is one very special type of vector, okay, and that's something called orthogonal vectors. Okay, so orthogonal vectors are perpendicular vectors, meaning the angle within them is pi over 2, right? Because orthogonal is perpendicular, right angle, so 90-degree angle is a cosine of pi over 2. Okay. So the consequence of this is if two vectors are orthogonal, if and only if, and this is a key thing, their dot product is actually 0. That's a nice thing going forward. Okay. Now, what does this actually look like in mathematics? Or why do we care about this? Okay. So the reason why we really care about this is because, well, if we want to find a vector that's orthogonal to the other, or maybe a vector that's orthogonal to two other vectors, we can actually do that. So because we're always going to be dealing with in 3 dimensions or a little higher dimensions because we learn algebra, we could say, well, if I have two vectors, so now I can find an orthogonal vector that's perpendicular to both of these. We'll call this like A. So this vector will be orthogonal to both these two here. Now, ironically enough, well, we know that if these two vectors, the dot product is 0, these two are orthogonal. But what if I find another one? And how do I find this particular one associated with it? And if we remember, well, this type of graph is called the cross product. So now, these two gives me a right angle, but what if I want to find another one that's also a right angle to these two here? That's how we find the cross product. And that's what's important about the cross product in linear algebra. So we'll go back to our definition of a cross product. So given vectors u and v in space, so 3 dimensions, the cross product is known as, like the times table there, is equal to this. Now this is difficult to remember, right? So I always go back to multivariate calculus and remember the component of a vector. So this is an alternative to it, and this is one probably the easier than the actual definition. It's just doing something, we'll talk about the determinant basically, right? So this is going to be I component, so cross, you see this component, and you do the process here, and vice versa. So something we've done in multivariable, we're just going to redo it here now. Okay. So then it's an alternative to doing this because that's a bit of a pain to do. So okay. Now the key thing is, right, we do get a vector out. That's a key component, right? So a dot product, we get a number out. A cross product, we get a vector because it's orthogonal to the other two vectors. Okay. So again, like everything else, let's try an example illustrating our cross product equation. Okay. So given the two vectors here, we want to figure out the cross product between them. Okay. So what I'm first going to do is convert this to look like that. And I'll do u first. Okay. And I will just follow this process. So if it's easier, just like I did to multivariable cross products, you cancel this out, and it's going to be this times this minus that times that. So this is going to be 2 minus this times this, so it gives you positive 3, so minus 3. Same thing in the middle, so we just cross out the middle and go crisscross. So 3 times 2 is 6, minus 4 times negative 1, so it's negative 4, so it becomes plus. And finally the last one. So this times this is negative 9, minus this times this is 4. Okay. So the cross product of u and v will be the vector of negative 1 negative 10, and negative 13. And again, actually, forgot. This should be a plus here. My mistake. Change that to plus. The middle is the negative. There you go. Okay. So there's a cross product, right? Just a little view of nice multivariable. And the next term is just the properties of what we can do with cross products. So unlike dot product, this is drastically different itself. It's not under association of cumulative property. It's actually none of these hold itself. So again, just nice little review of what they should look like going forward. So the nice thing is, well, I can ask you in a couple ways now, based off what we're given in linear algebra. So let U be this vector, let V be this vector. Calculate the cross product of these two. Okay. So if I do the same process, now if I do U first, so just remember this big of a trick question, right? I is negative 3. We have 0j and we have 6k, so just be careful. It has to have 3 components to it. And again, I just follow the same exact process. All right, so it's going to be 0 minus a negative 12, so it's positive 12. Negative 3 minus, looks like 6 times 4 is 24. This is 6 minus 0. So we get 12i. This is negative 27 minus negative, so positive 27j, and plus 6k. So you could leave it like that, or you could just give it to me in the vector format. And there we go.